Welcome, grade 10s. Today we have a jam-packed lesson. We're going to be looking at vectors and motion. It's part of mechanics. This is going to blow your mind. This section, grade 10s, I cannot emphasize enough how important it is, and I cannot emphasize enough how important it is for you to practice. We are going to go very, very quickly. We have a lot to jam-pack in this session. What are we going to cover? We're going to cover vectors and scalars, which are very important, and we're going to look at motion in one dimension, which means we're only looking at horizontal motion. Later on, we'll in grade 11 and 12, we'll add vertical motion, but for now, only horizontal motion. So let's jump right in. Vectors. Now, vectors and scalars are such an important concept for you in grade 10. It's the first time we've looked at this. So these are words and definitions you need to get, grade 10. You need to learn these definitions. The first thing is, what is a scalar? A scalar is defined as any physical quantity that has magnitude only. Magnitude means size. So it's things like time. Time only goes in one direction, okay? Only has size. Mass, which is measured in kilograms, only has size, okay? We often compare weight and mass together, because that's in the English language we talk about weight when we actually mean mass. Weight is a force, which is actually what brings us to our next thing, which is a vector. A vector is a physical quantity that has magnitude, size, and direction. We need to know which direction it's moving in. First vector I've already mentioned, which is weight. It's also a force. Force is a vector. Another vector is acceleration. Okay? Now, acceleration we're going to deal with a lot today. We talk about acceleration and deceleration. Deceleration is just acceleration in another direction, okay, going backwards. When we talk about direction, we're also going to look a little bit later on what we mean by that. Direction is so important. Okay, let's have a quick example. Let's classify the following as scalars or vectors. What that means is, do I ever look at whether I need a direction for it? So length, that's a scalar. If I tell you that, that's a scalar, not a scalars. Okay, it's a scalar. If I tell you that something is 30 centimeters long, there's no direction. I've just told you from end to beginning. That's easy. Force is a vector. Now, unfortunately, most of the time when we talk about I push someone with a force of 20 newtons, we don't always recognize that the push is the direction. Or I pull someone with 30 newtons, pull is the direction. Push and pull, it's two different ways, okay? Velocity is also a vector when it comes to that, because we need to know what direction it goes in. The next one's a bit of a silly one, but it's there. Direction is a scalar, it only has size. Well, it doesn't have direction, actually. Height is a scalar. So when we talk about how high I am, okay, how tall I am, which isn't very tall, by the way, it's just a scalar. We don't talk about the direction from the floor, which I'm quite happy with. Time, we've just dealt with. That's also a scalar. Actually, knowing that time's a scalar is very, very important, because it means for us that we cannot get a negative time. Time cannot go backwards, as much as we would like that to happen sometimes, okay? Time can't go backwards. Speed is a scalar. You've already dealt with speed because you did wave, sound, and light. You looked at the speed of a wave. We didn't consider which direction it was going in, whether it was going up or down or left or right or whatever. Temperature is a scalar. We can get negative temperature, but that's just the value. It doesn't mean that the temperature's gone backwards, okay, or gone forwards. It just has size, okay? Now, how do we show a vector? This is important. This is a new thing for you. Vectors are shown with arrows. So, if I draw an arrow here, that represents a vector. Let's say this represents a force of 12 newtons. The size of my arrow, the length, shows the 12. The arrow shows me the direction. Okay, so we point it in the right direction. If I tell you that I go for a walk and I walk 3 kilometers north, oh no, let's draw it with an arrow, sorry, that's not what I want. 3 kilometers north, there's my arrow, I'm going north, it's pointing upwards, and this represents 3 kilometers. Now we can do this with accurate diagrams, which means we would need to use a scale. Obviously, I'm not going to do that. That's a skill you guys need to go home and learn. If I told you to draw a 3 kilometer arrow pointing upwards, going north with a scale of, say, 1 centimeter equals a kilometer, then this would be 3 centimeters long. Okay? Scales are up to you. It doesn't matter. Point is, the arrowhead, which we always draw at the end, shows the direction. The size of the arrow shows the length, shows the magnitude, okay? And this is for any vector, whether it be vectors like velocity, acceleration, displacement, which we're going to deal with, any vector, force, all done the same way. Now, we've been talking about direction. What does that mean? We can describe direction in a lot of ways. We can say that it's going left. We can say it's going right. We can say it's going up. And we can say it's going down. These got a little off to the side, but it doesn't matter. Those are nice and simple directions, okay? Left, right, up, down, those are easy. However, we can also do it in terms of compass, points, and bearing. Now, I need to remind you that in a compass, it goes north, south, east, and west. Please be careful. If something's going to the left, you can't describe it as going west unless I tell you it's going west. You must describe your direction in the same way that your question describes your direction. So don't change it to north, south, east, west instead of up or down because you remember compass bearings, okay? And don't describe it as up and down when they tell you it's in terms of north, south, east, and west. All right, that's nice and easy. But we can also describe it in terms of bearing. Bearing's a little more difficult. What we need to remember about bearing is bearing starts at 0 degrees, and we measure bearing clockwise from the right round, okay? So east is at a bearing of 90 degrees, south is 180, west is 270, and we can get any angle between those. And they will say to you, for example, that Johnny walks 3 kilometers at a bearing of 40 degrees. Well, if I had to draw that in, we would measure 40 degrees and it would probably be around there. This is 40 degrees and I think I said 2 kilometers, I can't remember. He goes 2 kilometers at a bearing of 40 degrees. Okay, bearing isn't that difficult. It's measured from clockwise. Please be careful because it's, remember, on your Cartesian plane that you use in maths, 0 starts on the horizontal. Here 0 starts at the north line, so it starts at the top. Traditionally, north is always pointing up on your page, though it can point anywhere. You need to make sure I can see, well, your marker can see that when you draw diagrams, okay? Going really quickly, I know. What does this mean for us? Why do we need to know these things for vectors? Because we can get two very important parts in vectors. First, we get what we call the resultant vector. In other words, I take a whole bunch of vectors and I put them together and I look at how they interact and I go, well, if I had to take all those vectors away, whatever they were, and replace it by one vector that would do exactly the same thing, what is that vector? That's the resultant. Okay, so the resultant has the same effect as all the other individual vectors added together. Okay, we're going to look at how to calculate that in a second. The next one there is the equilibriant. You're not going to come across this often, but you are going to see it. The equilibriant is the vector that we would add to the system that would cancel out all the others. Okay? It's the same as the resultant, but in the opposite direction. So they cancel each other out. It's like two people pulling in opposite directions at exactly the same force. Okay? Nothing will happen. Resultant, adding all the vectors together, I can replace it with one. Equilibriant, the opposite of the resultant. Okay? Brilliant. Let's see how that all works in an explanation. Well, in a question. It says to us, determine the resultant force on a rugby player. So, if two players on his team are pushing him forwards with 60 and 90 newtons, and two players of the opposing team are pushing him backwards at 165. Let's put the equal sign in there. Okay, there's two ways we're going to do this. Head to tail. Head to tail means a diagram. Secondly, algebraically with an equation. So, head to tail is nice and easy. We've got F1, F2. I'm going to draw those in green arrows. We would draw this accurately. Okay, you would use a ruler, you would use a proper scale, you would make sure your scale works. Now, I'm not going to do it with a scale, but I am going to do it with arrows so we can see. I'm going to take forwards as going to the right because this is going to make it a little bit easier. So, F1 was 60, so here's my man. He's pushing forwards, that's 60 newtons. There, I'll put him, then I have 90. Obviously, it's a little longer. Let's just make sure they go right head to tail. Head to tail means that they need to be one after the other, okay, on top of each other. Let's label them because I need to know which ones they were. So that's 60 newtons. Okay, the little arrow on the top tells me that I'm dealing with vectors, by the way. Okay, so we really should write those in. Then the opposing team is 165. Let's do the opposing team in pink. Start where he was, and 100 probably goes to about there. Okay. Then we also have 65. So I'm going to draw in our second one. Let's make sure that, obviously, when you join this with your rulers, it's easier to make sure that they exactly head to tail. Okay. And this was F3, which is 100. This is F4, which is 65. So, the resultant is the arrow I would draw, which I'm going to do in white, starting from where my vector started, going to where they end, which is over there. Now, when you do this accurately, you would measure that line, and what you're going to see is that this line, and I call it the resultant, is 15 newtons. Okay? All depends on your scale. Remember, when you do something head to tail, so this is the first part, the bigger your scale, the more accurate it becomes. In other words, the bigger your diagram is, the better it becomes. You have limitations because of your paper. But don't draw this tiny little diagram that you need a microscope to look at, okay, a magnifying glass, because then you're going to be very inaccurate. The more accurate you are, the better. But how do I do this algebraically? This is actually really, really important. It's going to come up so often. First thing we have to do is we need to make a decision. We have two directions. Direction with vectors has to be a positive direction, and we have to have a negative direction. So I'm going to decide, because I tend to do this, the first thing they described to me was the rugby player being pushed by his own team, was being pushed forwards, so I'm going to make that my positive direction. Okay? Which means F1 was 60 newtons, and it's a positive value. F2 was also forwards, and that was 90 newtons, and that's a positive value. F3 was backwards, so it's in the opposite direction, so it's a negative value. F4 was also backwards and is also a negative value. So my resultant force is adding all of my forces together. Okay, so I have 60 plus 90 plus minus 100 plus minus 65, and you do this on your calculator, and you get minus 15. Hang on, right? Isn't that, look at that. We got 15 going backwards. We've now just got an answer of minus 15. The minus means it's going backwards. Vectors tell me I must have my answer as a positive answer with the direction in words. So that means my resultant is 15 newtons backwards. So the opposition's gaining ground here. Okay? 15 newtons backwards. Okay. Why is this important? Because this brings us to motion in one dimension. We're going to look at three very important definitions. Well, we're going to look at four different things here. First of all, we need to discuss what a frame of reference is. It's a reference point combined with a set of directions. When we were looking at this question now with the rugby player, the rugby player being pushed was our frame of reference. He was going forwards, he was going backwards. If I had made the team pushing the frame of reference, then things would have been different. Okay, we would have looked at it in a slightly different way. Generally, the Earth is our frame of reference, and you looking at the situation as it's happening is our frame of reference. Okay, position. Symbol X. When we look at change in position, it's delta X. Position is measurement of a location, all very fancy words, with reference to an origin. All position means is that if I tell you you have a position that is 3 meters south of me, you have a position. Position would be a vector. Okay? Position, displacement often get put in together. Measured in meters, SI unit, not kilometers. Distance, now make sure you see the difference here. Distance is a scalar, okay? Distance, I do not care which direction you went in. So for example, when you look at the Comrades Marathon, they will run 100 kilometers distance. From Durban to Pietermaritzburg to Durban, whichever way around they're doing it. But if I had to take the direction into account, it's actually less than if I take what we call the displacement, which is our next definition, okay, and I draw a straight line from Durban to Pietermaritzburg, that displacement, that straight line is shorter than 100, okay? So the displacement is less. Distance, I do not care about direction. It is a scalar. I only want to know the actual physical length of the path. Displacement, okay, and so let me just do this quickly before I get to displacement. D. We're not going to use, distance. We're not going to use distance very often. Displacement is change in position, delta X. We use X because we're only dealing with horizontal displacements at this point. When you get to grade 11 and 12, we're going to deal with vertical, and then we're going to change that to delta Y because it's position on a Cartesian plane, okay? It is a vector. Displacement must have a direction. Must have a direction, okay? Displacement is often smaller than your distance because displacement is a straight line. So to illustrate this, if we had a runner do this, goes on a race, has a curly race, gets to the end here. Their distance is the green line. I don't care how they got there, that we don't care about the displacement, we don't care about the direction, but if I had to draw their displacement in, it's the pink line. Displacement from beginning to end. Both are measured in meters, okay? Distance is a scalar, displacement is a vector, displacement needs a direction. Okay, let's look at an example for those. Use this figure to answer the following questions. And what they say to us here is, Jorge, it's a good thing I chose words I could actually pronounce, walks to Cosma's house. So she goes left. We're now going to choose, just because that was my original direction, left as positive. So anything happens to the left is positive, okay? She walks to Cosma's house, and then she walks to school. So that's 100 meters plus 100 plus 100 plus 100. So nice and easy. Her distance, we don't actually care which direction she went in, is 400 meters. Now they want displacement. Her direction is important. We have decided that going to the left is positive. So her delta x, she went left for 100 meters first, and then she went another 300 meters. So she went 400 meters left. We have taken her house as our reference point. Remember, we spoke about a reference point? We've taken her house as the reference point. In fact, that's what we're going to do for all of these questions for this section, for this particular example, is whoever's house we're starting at, that's our frame of reference. So she's gone 400 meters left from her home. Let's go to another one. Example 2. Now, Kolo walks to Cosma's house. So we're starting here, and she walks 100 meters to the right. Then she walks to school. So she goes 100, 200, 300. So her distance, where we don't care about direction, is 400 meters. Same as her friend. Let's look at her displacement though. Remember, I said to you going to the left is positive. She starts by going to the right, which means her first displacement is actually minus 100 because she went to the right first. Then she goes left 300 meters. So she actually has a displacement of 200 meters to the left from her home. Okay? And if we had to cancel out, if we look at it here, this is actually her displacement. She started here and has ended here. The first part cancels each other out. So for vectors, she really did nothing for the first 200 meters, which is a little irritating. But anyway, number C. Now we have Homal works, so we're going to go from him. He walks to the shop, 1, 2, 3, 4, 5, then walks back to school, 6, 7, 8, 9, 10, 11. So his distance is 1100 meters. Okay? So he went 500 meters right, and he went 600 meters left. Displacement. We just said he went 500 meters right. Remember, right was our negative value. And 600 meters left. So his displacement is actually only 100 meters left. Because, in reality, okay, I don't think you can see that. This is his displacement. Start, finish. The fact that he did a kilometer to the school and back to his house, to the shop, sorry, and back to his house really meant nothing. That is actually not important. Now, with all of these questions, I used their house as my reference point. We could have said use the school as the reference point, okay? But that would have just made it too complicated and really would have just made things horrible, so we don't do that. Generally, our starting position is going to be our reference point. Okay, so why is that important? Why is that important? Because we need to know distance and displacement for speed and velocity. Speed is a scalar, and it is the average, if we're looking at average speed, it is the average distance divided by the time taken, measured in meters per second. In this section, we're not going to use speed very often, okay? We generally are only using average speed as well. Average speed, no arrow on top of the V, okay? SP is not a symbol for speed. Do not use it. Average velocity is displacement divided by time. It is a vector, okay? We should have an arrow over there. It is a vector. It must have direction. Must have direction. So important here. Please remember that. Then we have two other really important concepts which we're not going to spend too much time on, but you do need to know what they are. Instantaneous speed is equal to instantaneous velocity. Makes sense. In magnitude. Instantaneous velocity is the change in position in a very, very small time period, where time gets very close to zero. Obviously, it can't be zero, grade 10s, because if I divide my equation by zero, it becomes undefined. You can't do that. Very small value, very, very, very small. We don't often work with instantaneous velocity at school level because of how small the t needs to be. And in fact, the easiest way around that is to use a branch of maths called calculus. You're not going to learn that till grade 12, so don't worry about it, okay? Last concept quickly, and then we're going to take a break. Acceleration. Acceleration, rate of change of velocity. Acceleration is very much a vector, okay? You are often going to get positive acceleration and negative acceleration. Negative acceleration generally will mean that an object is slowing down, but it doesn't have to. It just means that it's accelerating in the opposite direction to what we chose as the positive direction. Okay, but it is a vector. You are going to have to deal with it as a vector, so we need direction with it. Okay? Lots of stuff. So you need to go get a glass of water, take a break. We're going to deal with graphs when we come back, so I'll see you in a couple of minutes. Welcome back, grade 10s. We're going to go into graphs of motion. Now, guys, we're really a bit pressed for time because this is just a revision lesson. Guys, you've really got to spend some time developing the graphs and going through them and learning how to draw accurate graphs because you can be asked them. Graphs of motion are really important because it's a good way for us to describe motion in one dimension. Okay, motion that's happening, cars moving, balls bouncing, all sorts of things. It's such a good tool for us. So what we're going to do now is we're just going to go through the basic shapes and the three types of graphs you can draw. Please, grade 10s, you need to go back and relook at how your teacher taught this to you in terms of really getting all the detail in there. So when we have graphs of motion, we can basically draw three types: a displacement time graph, a velocity time graph, and an acceleration time graph. There are only three types of motion: stationary objects, uniform motion, which means acceleration equal to 0, and motion with constant acceleration. So that means my object can be speeding up, it can be slowing down, but the acceleration value stays the same. When we look at a stationary object, that means it's not going anywhere. That's the easiest out of all the graphs, because no matter how long we sit there, we just sit in there. So it's a straight line, horizontal straight line at one position. So nice straight line, nothing difficult. It also means, because it's stationary, that my velocity is 0. Please don't forget your to label your graphs, very important. It also means if velocity is 0, acceleration is 0. Straight lines, nothing difficult here. Uniform motion means that my acceleration is equal to 0. Does not mean that the object is stationary. It means that it's moving at a constant velocity. So when we draw this graph, it means that every second my object changes by the same value. So if it's going, say, at 12 meters per second, every second my object is moving 12 meters, which is nice because it becomes a straight line graph. Velocity is constant, so it's also a straight line. Acceleration is 0, okay? Now we get to the fun part. When we have an acceleration, in this particular example, I'm dealing with an acceleration that's positive. If it's a negative acceleration, your graph just gets flipped upside down. Accelerating means the velocity is increasing. If my velocity is increasing, so say we're going at 1 meter per second first, then we're going to go at 2 meters per second, then we're going to go at 3 meters per second, then we're going to go at 4 meters per second. That means in the first second, I go 1 meter. In the second second, I'm going 2 meters. In the third second, I'm going 3 meters. So every second I cover more and more distance, which is why my graph curves like it does, okay? The curve shows me that as the time periods get shorter, the distance I travel gets more. It is a curve, okay? Also means that my velocity is increasing, but at a uniform rate, so it's a straight line, and now my acceleration has a value. What you need to remember here, grade 10s, is that it is possible for all of these to be negative graphs. It all depends on your frame of reference. So we can flip them all the other way around, and you're going to see that from time to time. Though generally that would go into the extension, and we try and keep it nice and simple. But why are graphs so important? Because we can get so much information from them, okay? We need to be able to interpret these graphs, okay? From a position time graph, if I take the gradient of the graph, it gives me velocity, okay? The gradient of a displacement or position time graph gives me the velocity. We'll talk about gradients again in a second. For acceleration, okay, if I look at the area under the graph, now these two don't have an area, but this area here, that gives me velocity as well. Okay, fairly useful. My velocity time graphs are actually the most useful because the gradient of a velocity time graph equals the acceleration, and the area under the graph, so this area here, is equal to displacement. That's very important because it means that we can get not just information about displacement or velocity or acceleration, as the case may be, but we can get other information from the same graph. That makes these extremely useful tools for us, okay? Let's do a question, because the best way to work through these is with a question. First one, a bus travels at a let me change that to one I know you can see, constant velocity of 12 for 6 seconds. Constant velocity means acceleration is 0. He doesn't change direction. He doesn't go backwards. This is great. We're going to draw 3 graphs. Displacement time, velocity time, acceleration graph. Label all the axes. These are sketch graphs. Okay? Sketch graphs mean I do not need to do them accurately. It does not have to be to scale, but you still have to use a ruler, and you still have to put in any information you know. Okay, any information you know. So, position time graph, displacement time graph. Displacement, delta x in meters. Time, delta t or t in seconds. We know that it starts at 0. Constant velocity, acceleration is 0. Velocity didn't change. That means uniform motion, it's a straight line, and it's going to obviously get further and further away from where we're going. So we need to draw this in as a straight line. I don't want one with an arrow. So I'm just going to quickly change this because I don't want an arrow on it. And let's make it yellow. Okay. So there's my straight line. Okay. Now, I didn't know how far it goes. What value can I add in here, though? Because I do know that value is I did this for 6 seconds. That's all I can add in. I didn't work out the displacement. They didn't ask me to. They might ask you to later on. We're going to look at that when we do equations of motion. Though this one's actually quite simple because remember, earlier on, we did that velocity is change in displacement over change in time, that it was going at 12. Displacement was 6. So it's 12 times 6. Let's just work that out. 72. Okay, so it's at 72 meters, which means I could add in here 72 meters. Okay? If you were asked to write it in. So it's something we could add in. Wasn't difficult. Next graph that we're going to draw is our velocity time graph. So I'm going to do my axis this way. It's a bit easier. And time. You know that's going to be 0. Once again, straight line, uniform motion. We also know, okay, let's change my arrow again. Didn't want to stay that way for some reason. There we go. Straight line. There we go. And 12 meters. And that's for 6 seconds. Straight line. Last graph is my acceleration time graph. Okay. Also at 0. Now we said it was going at constant velocity. Constant velocity means 0 acceleration. So my line, and I know you're going to struggle to see that, unfortunately. So this is where you learn that. You're going to have to make sure your examiner can see it. We would maybe make this line, let's just do this, make this line a little thicker so you can see it. There we go. Okay. But it's on the 0 point. So over here, we would make sure it goes from 0. And I'm just making it really thick so you can see it, and you would do the same in your test or exams. Please, you draw graphs in pencil, label in pen. Very important. Okay? Nothing difficult about that question. All right. Now, let's go on to a nice question. A velocity time graph for a ball rolling down along a track is shown below. Here we have our graph. It's divided into 3 sections. They're really nice for us because they tell us this is section A, section B, section C. Now, what does this graph tell me? Let's just work through it before we actually answer any questions. It's a velocity time graph. So my ball starts at 0, accelerates to 0.6 in a certain direction. Okay, that's great. For 5 seconds, then it goes at constant velocity for 0.6 seconds, for 5 seconds till it gets here. Then at this point, it slows down and then eventually changes direction because this means it gets to 0. Okay, it's on the 0 line, and now we end up at -2, so it's changed direction. So the ball went in one direction and then changed direction for the last however many seconds it is, because I don't know what T1 is. Okay? Use the graph. Use the graph. Please, grade 10s, I'm begging you. When you get questions like this, often you may use the graph or equations of motion to solve the problem. because that's the way the graphs work. But if the question says to you, use the graph, and you use equations of motion, you will get naught for that question, because you've got to follow the instructions. We are testing a skill. Okay, be careful. My learners do this all the time, and then they moan and they cry, and then I can't give them marks, and I want to smack them because they didn't listen. Okay, so use the graph. First question. To determine the speed, direction not important, 5 seconds after the start. Okay, well, let's go to the graph. There's 5 seconds. We go up. Oh, look, it's marked for us. It is. So my speed after 5 seconds, 0.6 meters per second. Yay! Done. Easy. Question 2. The distance traveled in section A. Okay, section A. In other words, 0 to 5 seconds. Now we've got to think back to what I said to you earlier. From a velocity time graph, I can calculate acceleration using the gradient, and I can calculate distance using area. So if I'm looking at section A, that's this section here. Oh, look at that, it's a triangle. How do I lay this out though? Very important. So this is question 2. Watch, so important. Distance is equal to the area under the graph. That is the equation. Okay? You can't start with the equation for area, because distance doesn't equal a half base times height or length times breadth or whatever the case may be. Distance is the area under the graph, which happens to be a triangle. So that means it's a half base times height. Please, grade 10, you need to go back to some of your basic maths and learn how to work out the area of a triangle and a rectangle, because you can always split your graphs up into those two shapes and then add a whole bunch of areas together. So look at it. We go, my base is 5, my height is 0.6. So it's a half times 5 times 0.6, and we get 1.5 meters. It's actually going relatively slow if you really think about it. It took 5 seconds for it to travel 1.5 meters. That's not very, very far at all. You all happy with that? Good. Next one, the acceleration in section C. That section. First hint that you need to recognize here. It's going from a high acceleration, 0.6, gets to 0, changes direction. My acceleration answer must be negative. It's also a negative slope on the graph. You can see that. It's a lazy graph. It's going to sleep. In section A, it would be positive acceleration because it's a happy graph. It's working. All right. Let's look. Number 3. Okay. We want the acceleration. My acceleration is equal to the gradient. Now, this isn't maths, first of all, but we're using maths principles. You know, in maths, gradient, some of your teachers might have taught you this, is rise over run, okay? And it's equal to m. Please don't use the symbol m, because not all your teachers will understand what that means at the end of matric, okay? Don't use m. Use gradient. Use the word gradient. In maths, you would then say to me, you would go, rise is y, so you go y2 minus y1 equals divided by x2 minus x1. We have not got y, and we do not have x as the point on this graph. This is a velocity time graph. We're going to use v2 minus v1 over t2 minus t1. In maths, you may choose any 2 points, and you may go backwards, forwards. It doesn't matter. You may not in science, because time can't go backwards, cannot go backwards. So what I'm saying to you is that point at 12 seconds must be T2 and V2. That point at 10 seconds must be V1 and V2 and T1, okay? So in other words, we're going to go T2, V2 was minus 0.2, started at 0.6, 12 to 10, so we get minus 0.8 divided by 2 minus 0.4 meters per second squared. Don't forget the units. The minus is fine. All that means is that the acceleration was in the opposite direction to the motion. And don't say it's 0.4 meters per second squared slowing down, because it's not always slowing down. It's slowed down, stopped, and then changed direction. So it slowed down, then sped up, but it still has the same acceleration. The negative just means that your acceleration was in the opposite direction to which it was moving. All right? Then, next question. Here, I want to leave that one out. We're going to go to here. Sketch a displacement time graph for the motion of the ball for the 12 seconds. They're very nice here because they say to you, you do not need to calculate the actual values of the displacement, but you do need to pay attention to the general shape. Yay, we like this. If they were being really mean, what they could have asked you to do, and we already know, for example, that that was 1.5 meters, so we're halfway there, is they could have asked you to put in all the values, but it's still a sketch graph. So you would have had to sit and go, okay, A went 1.5 meters, B actually works out to be 1.2, and then you would have to work out C. Don't need it, not important, they just want the shape. You do need to add in the 5, the 10, and the 12, okay? Right, let's do this, shall we? Displacement time graph. And now I've taken the arrows away, let's use here. Okay, displacement time, okay. So this is my displacement. Let's write it in nicely. And I'm going to need to quickly do something because I realize this is a problem. Sorry, I'm going to move this here. You'll see now why. Okay, there we go. Let's just move this here. Okay. On our time, we did have some time periods that we knew. So we knew, for example, that we have something that happens at 5 seconds, something that happens at 10, something that happens at 12. And now what I'm going to do, I'm just going to make my life a little easier, is I'm just going to draw guidelines here for me because it's going to make, so I can make sure I get it nicely drawn for you guys. So that's on 5 and that's on 12. You wouldn't need to necessarily do this in your exam. It's just to make my life a little bit easier. So for the first 5 seconds, our ball was accelerating, okay? It was getting faster. So what that means is for the first 5 seconds, my graph starts at 0, that's its reference point. Okay, it's accelerating, great. Then for 5 to 10 seconds, it has uniform motion, but it's not accelerating, but it's still going, okay? So now we actually need to draw this in as a straight line because it does that, okay? Then the last 2 seconds, it has acceleration, so it's still going to be a curve, but it gets back to 0 velocity and then changes direction, okay? We don't know if it actually goes past the displacement point. Okay, we don't know that because we haven't worked out the displacement, but we do know it's getting faster as it goes down. So what this means for my second graph here is now it's accelerating in that direction. Okay, you could go beyond 0, that's fine. We would actually need to work it out, which we haven't done, and I think it's safe to say because it didn't go very far, very long in the opposite direction, it's not actually going to go back to its starting position at all. So I just drew the negative in just to be on the safe side. If we had worked it out and we realized that it does reverse direction completely and does go in the opposite direction and goes beyond its reference point, okay, then I would have to draw this below the 0 line. But at this point in time, we're not too worried about it. What am I looking for? I'm looking for that you understood that shape because it was accelerating, getting faster, the straight line when it was uniform motion, and this because it's accelerating in the other direction. Okay? Wow. Graphs of motion, lots of hard work. Practice, 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 practice. We are going to take a short break, and then for the last section of today, we're going to look at equations of motion, doing a couple of problems because it's the best way to learn them. So go get a glass of water, take a break. We'll see you in a couple of minutes. Grade 10s, welcome back. Last section, last push. We really have done a lot of work today so far, and the last thing we need to deal with equations of motion. This section, and I know I've said it lots today, practice, 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 grade 10s. This, you can do it with me, and I'm glad you're doing it with me, and I'm going to go through some problems with you, but really you got to work through these problems on your own to really get it into your heads. We have 4 basic equations of motion which are derived from the graphs of motion. We're not going to spend any time on that. These equations of motion will be given to you on your information sheet, but the more you use them, the more you know them, the better you are at using them. And that's what we need to emphasize. The first equation is VF equals VI plus A delta T. Let's go through what all of those mean. VF is our final velocity, which is measured in meters per second. VI is initial velocity, so it's the beginning, measured in meters per second. A is acceleration, measured in meters per second squared, and delta T is time, measured in seconds, which is great. We're going to use that one quite often. The next equation is delta x equals VI plus VF divided by 2 over delta T. Now, delta x, oops, sorry, that's terrible. Delta x equals displacement, and displacement is measured in meters. I need to put a little bit of word of caution here, grade 10s. This equation is actually a very special equation and can only be used when the motion is 100% constant. So there is no change in the motion of the object at all, ever. Be very careful. I personally, and I've been teaching for about 15 years, I never use this equation. When I teach this to my learners in my school, I never use this equation, simply because it is too easy to use it in the wrong context, and then you get the wrong answer and everything just falls apart from that. Please try and avoid using it if you can. All right? Please, I'm begging you. Next equation. It's been written a little funny. I'm just going to correct it. That should be t squared. Delta x equals VI delta t plus a half a delta t squared. Unfortunately, the t went for a holiday. Then VF squared equals VI squared plus 2a delta x. Remember, the arrows on the top simply mean that they're vectors. We're not going to include them when we write anything down. VF squared doesn't have an arrow. It hasn't changed. Velocity is still a vector. It's just because when we multiply a vector with a vector, we get a scalar. You'll learn that at varsity. Don't stress. These 4 equations, very, very, very important. What do we need to remember? We're dealing with vectors, which means direction is important. Time can never be negative. Velocity, final or initial, acceleration, and displacement can all be negative. It all depends on what we choose as our positive direction. Choice you need to make. Very important here, grade 10s. Also, if you have a question with lots of little parts to it, and you choose forward, for example, as your positive direction. Forward is the positive direction for the entire question. You may not change that sign convention to something else in the middle of the question because it makes your maths a little easier. You may not do that. You will get naught. Okay? We're all right with that? Brilliant. You're ready to dive into a question. Question 1, which is now example 5. A racing car going at 20 meters per second. That means my initial velocity is 20 because that's what he's going at. Stops. Final velocity is 0. In a distance of 20 meters, they're telling you delta x equals 20. What is its acceleration? A equals, all right. We're going to need to go look at our equations. So now we need to decide which one to use. So we go back and we look at our list and we go, okay, let's see. If we look at the first equation, we go have VF, have VI, don't have T. Can't use that one. Have delta X, not that I want to use that, so I'm going to ignore it. Let's see here, I have delta X, I have VI, don't have time. Okay, leaves me with the last one. That's how we choose which equation to use, grade 10s. All right, until you know the equations, that's exactly how you do it. You go into your list, you tick it off, and you go, well, if I'm missing more than one, I can't use that equation because I don't have enough information. So let's go back. All right. VF squared equals VI squared plus 2A delta x. Please, another hint here for your exams. Don't manipulate this now, grade 10s. Substitute in what you know. Then do the maths. Final velocity is 0. Initial is 20. Okay. 20 squared. I'm actually going to do all the maths for you. So this becomes minus 40A equals 400. And there's our answer, minus 10 meters per second squared, which makes sense because that means it is decelerating. It's getting slower. Okay, because it's slowed down to a stop. Ready for something a little more complicated? Of course you are. Next one. Motorcycle has uniform acceleration, okay, that should be squared, sorry, of 4 meters per second squared. Okay, assume the motorcycle has an initial velocity of 20, so VI is 20 meters per second. They want to know what is the velocity, so that's final. What is the displacement at the end of 12 seconds? Okay, well, let's start with the easy one. We want VF, and we would go back to our list. We tick off what we know, and we're starting to learn the equations now. So I realized that I would need to use VF equals VI plus A delta T because it doesn't have displacement in it. VF is what I'm looking for. Great, we don't have to do any manipulation. So that's 20. A is 4. Time is 12. So we have 20 plus 48. 68 meters per second. It's going really, really fast, by the way. 68 meters per second. The third line that I've written, grade 10s, where I put 20 plus 48, you don't need to show that. You can do it on your calculator. I just want to show you all the maths. So now we have 68 meters per second. Now, grade 10s, I underline that because now I go, all right, I've got to find displacement, but if I can avoid using VF, then that's what I'm going to do. Because if VF is wrong, then my displacement's wrong. And I can avoid using it because I can use this equation. delta x equals VI delta t plus a half a delta t squared. So VI was 20, my time is 12, we have a half times 4 times 12 squared. Okay, so let me just show you how we would do it. So we've got 20 times 12, 240, plus we've got a half times 4 times 12 squared, 288. And just in case, I just want to show you, do not try and do this in your head if you struggle, and that's fine, 528. Now, what if you did decide to use your VF squared? I want to show you that it doesn't matter. You would use this equation. Okay, we worked out VF squared to be 68, well VF, VI was 20, A is 4, and we want delta x, okay? So now watch, let's put it over here, is we're going to have 68 squared, 4,624, 20 squared is 400, equal to 8 times delta x. We're going to take the 400 over, so it's 4,624 minus 400, so that's 4,224. Sorry, that should be a plus sign, not an equal. Okay, equals 8 delta x. So if we go 4,224 divided by 8, look at that, 528. All right, grade 10s, what am I trying to show you? It doesn't matter. There's always more than one way to do these problems. Find the simplest. Besides the fact that this way uses something I had to work out, it also has, the maths is a little more difficult. The first equation I used, I didn't have to do any manipulation because delta x was equal to the equation. No manipulation. Makes life so much easier, okay? And I'm lazy when it comes to maths. I don't want to have to do hard maths. I don't like it. Okay, let's do one more question. You guys are doing great. Car. Once again, we're looking at a car. Is driven at 25 meters per second in a municipal area. When the driver sees a traffic officer at a speed trap, oh dear, he realizes he's traveling too fast. He immediately applies the brakes while 100 meters away from the speed trap, hoping he's not going to get a fine. Calculate the magnitude of the minimum acceleration which the car must have, so we want acceleration, to avoid exceeding the speed limit, if the speed limit is 16.6. So, let's think about what information they're giving us. They're telling you his initial velocity is 25. They're telling you he needs to change that velocity in 100 meters. He needs to get to a final velocity of 16,6, and they want to know what his acceleration needs to be. So now we go, okay, I have VF, I have VI, I have delta x, I need A, and we go back to our list, we tick off what we know, and we go, okay, VF squared equals VI squared plus 2A delta x, that's what I'm going to use. VF being 16,6, VI is 25, and he wants to go 100 meters. So VF squared, this is 275,56. 25 squared is 625. That's 200A. You would minus 625 on both sides. gives me minus 349,44. I'm going to divide by 200, and my A is minus 1,75 meters per second squared. That's quite a serious acceleration, okay, because he's got to seriously slow down quite a bit in order to not get fined. That's the minimum acceleration. If he accelerates more than that, so say minus 2 meters per second squared, he will get to the 16.6 meters in a shorter time. Now they say, second part of the question is calculate the time from the instant the driver applied the brakes until he reaches the speed trap. So now they're saying to you, if he starts at 25, he's going to end at 16,6. We've just calculated his acceleration as minus 1,75 meters per second squared. He needs to do it in a distance of 100 meters. That hasn't changed. How long does he need to do it in? How much time does he have before he's going to reach the speed trap? So many ways to do this question. We know A. Let's do the easiest. VF equals VI plus A delta T. VF is 16,6. VI is 25. A is minus 1,75. Please, grade 10s, be careful here. That negative is important. It's slowing down. It's a direction. You cannot let it go on holiday. Okay. We're going to take the 25 over, so we get minus 8,4 equal to minus 1,75 delta T. We divide by minus 1,75 on both sides, and we get 4,8 seconds. Now I know I'm right because I've got a positive answer. If you'd left the negative out for your acceleration, you would have got negative time. That means he's going backwards in time, which I'm sure he would like, so he doesn't get his fine. But we can't do that in reality, okay? That is not possible at this point in time. Okay, so we've just finished this question. Now what we're going to do, grade 10s, is we're going to go back to a question, because here I've done equations of motion as just on their own in a nice question. But remember earlier today, we did a question with that graph. Do you remember the graph with the slope? Well, you know what? We can add to that. So what we're going to do is we're going to go back to that question. All right, so here it is. Do you remember we spent some time looking at this graph? We did a whole bunch of calculations, and then we did some graphs. But now, watch what this question says to us. Remember, it's accelerating and constant motion, then deceleration. It says to us, at T1, so at this point, the velocity time graph intersects with the time axis. Use an appropriate equation of motion to calculate the value of T1 in seconds. Now, grade 10s, the very first question here said to us, use the graph to calculate. Now we're saying, use equations of motion. That means I need to know time from here to here, 10 to T1. How long does it take? I cannot start this from 0 because the acceleration changes. There are 3 sets of motion. I'm going to start here. So what I'm going to do with this one is I'm going to say to you that from the graph, I realize that VI is 0.6. All right? I realize VF is 0. That's the trick here. We also, and I'm just going to remind you, earlier we calculated over here the acceleration to be minus 0,4. I still need to use that grade 10s. That hasn't changed. I've just added a little bit to the question. So this was minus 0,4 meters per second squared. So A is minus 0,4 meters per second squared, and what they want is we need T1. T1, not Ti, sorry. we think back and we go, okay, wait, we go through our equations in our head and we realize, oh, this is nice because it's a nice easy equation. VF equals VI plus A. I'm using T1. So VF is 0 and VI was 0.6. A is minus 0.4. In fact, I just want to make a small correction here before you do this. Let's take the T1 out for now. I'm going to explain to you in a second why I want to do that. Okay, and that's delta T. So we take that minus 6 over, minus 4. So now, delta T is minus 0.6 divided by minus 0.4, which gives us 1,5 seconds. We're not done. Careful, grade 10s. The question asked you to calculate the value of T1. T1 can't be 1,5 seconds because it's after 10. Okay? It took 1,5 seconds to go from 10 to T1. Please get this, grade 10s, which means delta T1 is 10 plus the 1,5. So that's 11,5 seconds. Okay, so we are done for now. So what have we done in this lesson? We covered vectors and scalars with their definitions. Scalar, physical quantity, no direction, just size. Vector, physical quantity, size, and direction. We can represent vectors using arrows where the length of the arrow is its magnitude, the direction is shown by an arrow. And remember, direction be left, up, down, right, or compass bearings, north, south, east, and west, or it can be bearing 40 degrees, 30 degrees, whatever the case may be. We then looked at graphs of motion, realizing we can draw velocity time graph, acceleration time graph, displacement time graphs, and we looked at the shape, which means you need to go back and relook at those shapes because they're very, very important to remember. We only use constant acceleration, uniform motion. And then we ended off and we did some calculations of that, before we got there, and we realized that from a displacement time graph, we can calculate velocity from the gradient. From a velocity time graph, we can calculate acceleration from the gradient and displacement from the area, and from an acceleration time graph, we can calculate the velocity from the area under the graph. Then we went on to equations of motion, and really we've just worked through some of the equations, realizing that we've got to take negatives into account, all about interpreting the question. We could do hundreds of these. We really could. The more you do, the better you get. Okay? Practice, practice, practice. Grade 10s. And we are going to end it there for this session. I really hope this was helpful, and we'll see you again next time.